Today we're covering the Chapter 4 review questions from Berean Builders Discovering Design with Physics. As usual, I am not going to cover questions that are quite easily found in the book that are really just about definitions. And number 1 doesn't look like it, but it is. And it's in one of the pink boxes in the book is the answer for this. So I'm not going to cover this one. We're just going to skip straight ahead to question 2. Question 2 asks us, is the magnitude of a vector ever negative? And I'm not going to write this one down. I'm just going to tell you what I think verbally. And the answer is no. Magnitude is a scalar quantity, and all scalar quantities are positive. Question 3. A student writes a velocity vector as 4.5 meters per second at 45 degrees, negative 45 degrees. What is wrong with the way the student is reporting the vector? Well, the big thing that is wrong with this is this negative 45 degrees here. The degrees cannot be negative. This direction must be represented by a degree number that is between 0 degrees and 360 degrees. It cannot be negative. So this angle is incorrect in this problem. Question 4. Which of the following could represent a velocity of 15.0 meters per second at 256 degrees? So let's think about our quadrants, and I'm just going to play on this one to demonstrate. So going east, this degree level is either 0 or 360. Okay, going straight up would be 90 degrees. To the left is 180 degrees, and down is 270 degrees. So with an angle of 256 degrees, we know that we are between 180 and 270 in quadrant 3. And so our answer has to be in quadrant 3. We actually have 2, though, that are in quadrant 3, B and C. And so let's look at the value, 256 degrees. Well, this is much closer to 270 degrees than it is to 180. And so this C answer is the most correct. For question 5, this question is incorrect as per the errata for the book. And so the correct question, the way the question should be written here, I have marked out the incorrect and typed in the actual correct question as per the errata. So suppose the correct answer to number 4 now represents a force of 15.0 newtons at 256 degrees. What would have to change for it to represent a force of 7.5 newtons at 256 degrees? Okay, so the angle didn't change. They changed it to newtons instead of meters per second. Not a big deal. And so it's saying now this represents 15.0 newtons at 256 degrees. How would it change if it instead represented a force of 7.5 newtons? Well, the length of this arrow represents the magnitude, which is this number of force here. And so the length of the arrow would have to be half as long. I'm not going to write that down, just telling you what the answer is on that one. Question 6. Given vectors A and B on the right, draw A plus B and A minus B. So for these, we're going to draw our own graphs. So, because otherwise this would get way too messy. It's not really big enough. So, and we're going to first draw A. And it may not be exactly the same angle, but it's okay. We're still going to get our point across with this. Okay. Now next we need to draw B. And when we are doing these, when we do A plus B, we're going to add B to A. Okay, so where A ends, B needs to begin, and begin at the same angle that it is coming from the origin point here. Okay, so approximately same angle, same length as, and this is bigger than this, but you know, same relative length is where B is going to be. So this is A plus B. Now A plus B would then equal C, or in this case, we're just saying A plus B. And so this final end point here, that is the sum of A plus B. And we're going to label it as such here. Okay, so that's the first one, A plus B. Now for A minus B, this is going to be the same thing as A plus negative B, okay? And so what is negative B? Well, that's just going to be the inverse line of this one. So we basically just do a 180 and draw that out. And this is minus B, it's negative B, okay? And so now we're going to draw this on our own graph. Okay, so we'll have that same A. Okay, and instead of our plus B going like this, we're going to have a minus B that is continuing from here to here. And we're going to label this minus B, okay? And so now A plus negative B is going to be the line from the origin, which is, I don't have a great line here, but from the origin to where the negative B ended. And so A minus B is how we'll label that, right? And like I said, these may not be exactly to scale to this or exactly the same angles, but what we're doing here is just getting, showing the idea of what A plus B and A minus B look like based on this graph. Okay. So now for question 7. It says one force acting on an object is 10.0 newtons at 105 degrees. A second force of 5.0 newtons at 180 degrees is acting on the same object. If those are the only two forces at play, which of the following answers show the net force? Okay, so what we're basically doing here is this force is A, and this second force is B. And we're going to say A plus B and figure out what which one of these is C. Okay, so let's draw our own graph. Okay, and just remember that this is 90 and this is 180. Okay, so our first force is going at an angle of 105 degrees, and it is double that of the second force. Okay, so 105 degrees, we're going to say it's just roughly about here. Okay, doesn't have to be perfect, but roughly about that. Okay, we're going to label that A. Now our second force is half the length of it, half the magnitude, and it's going 180 degrees. So 180 degrees, if I drew it from the origin, it would be just along the x-axis. But we're going to draw it starting from the end of A because we're adding A plus B. And so it's just going to be a horizontal line that is roughly half the magnitude of A. And so this is B. Okay, so now A plus B is this line, and we can call it C. Okay, so which of these is equivalent to this, and of course, the only one that looks even close is B. Now question 8, what are the x and y components of an acceleration of 3.47 meters per second squared at 301 degrees Celsius? Okay, so this is our main magnitude and direction that we are determining. And what we're looking at as far as a graph here, okay, we have 301 degrees. So remember, this is 270, this is 360. Okay, so we're roughly a third of the way over on this, and so this is what that looks like. Okay, and we are determining what the x and y components are for that. So to do that, we're going to use our equations 4.1 and 4.2. Okay, so 4.1 tells us that our y component is our line here, right, or magnitude of that line there, times the sine of the angle. Okay, so plugging all that in, we have 3.47 meters per second squared times the sine of 301 degrees. Okay, then with three significant figures, our answer is negative 2.97 meters per second squared. Okay, and that tells us why we are going down 2.97 meters per second squared. We'll do the same thing for our x component, except for this one we're using equation 4.2, and so for that we have we still use the same magnitude, but we're going to use cosine on the angle instead of sine. So I didn't write out the full equation without numbers, but it's basically the same except we use cosine. Okay, and that ultimately gives us, with three significant figures, 1.79 meters per second squared. Okay, and those are our answers. The x component, I'm just writing it in the same order that the question asked it, even though I did them did the work in an opposite order. The x component is 1.79 meters per second squared, and the y component is negative 2.97 meters per second squared. And that's my answer. Okay, question 9. A person walks 3.66 kilometers due west and then 2.14 kilometers due north. What is the magnitude and direction of the person's displacement vector? So let's draw a graph. Okay, so first they are walking west. So east is positive on our x-axis and west is negative. Okay, so I'm going to go ahead and draw an arrow there. Okay, and I'm going to label it negative 3.66 kilometers, right? Because west is going to be negative on the x-axis. That negative is really important to this problem. Then I'm going to draw another arrow going north, 2.14 kilometers. And of course, north is positive. So we're not going to change the sign on that. Okay. And so what I am trying to determine then is the magnitude and direction of those added together. So what is this line? Okay. So for this, I'm going to determine the length of this line, the magnitude, and I'm going to use equation 4.4 for that. And then I'm going to determine the angle that this is at, and I'm going to use equation 4.3 for that one. So let's do the magnitude first. And so just as a refresher, that equation is A equals the square root of, AX squared plus AY squared, right? This is a formula for a hypotenuse. And plugging everything in here, so my AX is negative 3.66 kilometers squared. Make sure this is all under the square root sign. And my AY is 2.14 kilometers, and we're going to square that. Now, whenever I am doing these hypotenuse equations, I'm always going to determine the squares first before I add it and do the square root. I'm going to do each part separately, and the reason for that is keeping my significant figures in line. So you'll see what I mean as we go through these problems. Okay, so my negative 3.66 kilometers squared, we're keeping 3 significant figures since we're multiplying this times itself, and that comes out to 13.4 square kilometers. And I actually don't need parentheses here. 13.4 square kilometers plus 2.14 kilometers squared. Again, 3 significant figures. I'm going to end up with 4.58 square kilometers. So notice here that one of these, to get 3 significant figures, I'm at the 10ths place, and the other one I'm at the 100ths place. Well, my rules for addition with significant figures is that ultimately my answer is reported to the least precise significant figure of the things that I was adding. All right, so my answer from these two is going to only be to the nearest 10th. So when I add 13.4 plus 4.58 and then round it to the nearest 10th, I'm going to get 18.0 square kilometers. Okay, then I can do my square root, and with that I'm back to multiplication rules, and I'm going to have 3 significant figures. Oops, I don't need the square root sign anymore. And so my answer for my magnitude is going to be 4.24 kilometers. Okay, so now let's determine the direction. So for the direction, we're going to use equation 4.3. And as a reminder for that, it is tangent of the angle equals AY over AX. A good way to remember that Y is on top on this and X is on the bottom. It's just think about slope, and we have rise over run, and so the Y values are over the X values when we do slope also. So my Y value is 2.14 kilometers. My X value is negative 3.66 kilometers. Okay, and rather than divide this first, I like to go ahead and move my tangent over to the other side. And so I'm solving for, instead, my angle equals the inverse of tangent times that value. And the reason why I do that is because you're going to want to go out way more decimal places than you actually need to for significant figures here, because you know, tangent, sine, cosine, they're all so affected by the very smallest decimal places. and it's not necessary to actually stick to 3 significant figures at this step, because you're doing lots of division here. And so you can just get it to 3 significant figures at the very end instead. Okay, so when I do that and I calculate the inverse tangent of all of that, I'm going to get negative 30.3 degrees. Now, this is not an accurate number. As we know from that previous problem, we can't report a negative, right? We also know that based on what quadrant we're in, we're going to add a certain amount to the calculated value that we get for this. Okay, so this is that rule, right? And from here, it looks like we are in the second quadrant, but we can also, just confirming that, right? We have a negative x value and a positive y value, and that equals quadrant 2. So we're going to add 180 degrees to this. And when we're determining significant figures, this 180 is an exact number, so it plays no role in determining any significant figures. The significant figures are still completely based off of this number. So when we add 30.3 plus 180, we get 149.7 degrees. So our final answer is the magnitude is 4.24 kilometers, and the direction is 149.7 degrees. Okay, and that's it. That's question 9. Question 10. A man in a rowboat is crossing a river. The river's current is due east. The man wants to land directly south of the place from which he launches his boat. Which of the following angles for the rowboat's velocity would possibly allow him to reach his goal? So I'm going to draw some pictures on this one to help me out. So we have a river here, okay, and the river's current is due east, and he wants to land directly south. So he is leaving here. Here's my very crude drawing of a boat, okay? It's not good at all, but we're leaving here, and he wants to land here, okay? So in the convention that we use in this book, or that Dr. Wile uses in the book, the A line is what the engine or the boat is doing. The B line is what's affecting it, and the C line is what happens as a result, okay? And so we want this to be our result line, so I'm going to call it C, okay? And this B is acting on C, and it's going east, okay? Which means it needs to be to the left of the C line so that it ultimately hits the C line at the end point, okay? So this is B. We don't really know what the magnitude of any of this is really, but we'll go ahead and draw it, okay? So this is what's happening. And so we know then that to get from here to here, we're going to have to actually move this direction, right? Because the current will be pushing the boat as it goes across, okay? Now, like I said, we don't know what the magnitude is. So, this could look more like this. Here's B, and here's C, or here's A, right? This would be A, all right? Or it could even look more like this. B is really small, right? If that current is not moving very rapidly, okay? So that angle of A could be very, very different depending on what this magnitude of the B is, how fast that current is, okay? But what is the same no matter what is that the angle of this A is in quadrant 3 of our graph, okay? And so therefore, our angle value, 180, has to be between 180 and 270, okay? And 270 itself will not work because this B is moving, right? And so if this A went straight down, the B would be pushing it down into quadrant 3. So which of these is between 180 and 270? And that answer is D. Okay. Question 11. Displacement vector A is 5.66 meters at 235 degrees, and displacement vector B is 3.89 meters at 115 degrees. What is the sum of those two displacement vectors? Okay, so like I keep telling you, I want to draw a graph. So that's what I'm going to do at the start of all of these, just to give myself a visual representation of what I should be expecting. Okay, so my A is 5.66 meters. My B is 3.89 meters. That gives me an idea of like what I should have as far as proportions of my dimensions. And 235 degrees is A. Okay, so for A, I'm drawing a line that looks about like this, and it's going to be the longer line because it's much more than B. Okay, and it's going about 235 degrees. Okay, then displacement vector B is 3.89 meters at 115 degrees. So 115 degrees is going up like this. I'm going to go ahead and draw about what that looks like, going from the origin. Okay, so this is A, this is B. Now I'm going to draw it as an A plus B. About like that. Okay, and then from there, I'm going to draw my C. So like I said, this just gives me an idea of what I should be expecting. So now we're going to then start using our equations 4.1 through 4.4 to figure out what the sum is of these displacement vectors. Okay. So I'm going to start with AY. Okay. And so AY equals A times the sine of that, right? That's just giving me, you don't really need to write this down. If you know what the equation is, you can just go right into it, okay? But my AY equals 5.66 meters, right, from here, times the sine of 235 degrees. Okay, that's going to equal negative 4.64 meters when I calculate that out. Now I'm going to do my by. By equals, I'm not going to rewrite any like initial equations here. I'm just going to start plugging in numbers. 3.89 meters times the sine of 115 degrees. Okay, and that to three significant figures is going to be 3.53 meters. Okay, now let's do our x values. So as a reminder, ax equals a times the cosine of that angle. So my ax equals 5.66 meters times cosine of 235, and three significant figures, that ends up being negative 3.25 meters. And I'll do my bx, and it's going to be 3.89 meters times cosine of 115. And three significant figures, we will get negative 1.64 meters. Okay, so now I have both of my given y's, both of my given x's, and from this I can now determine c. So c of y or x is going to be the addition of them, all right? So cy is going to be negative 4.64, and that's meters, plus 3.53 meters, and we'll get negative 1.11 meters from that. I'm going to go ahead and do my x. So my x value is going to be negative 3.25 meters plus a negative, so I'm just going to say minus 1.64 meters. And with that, I get negative 4.89 meters. Okay, so now that I have my x and y value, I can determine what my actual c vector is. Okay, and so that with that, I'm going to use equation 4.4. We're getting the hypotenuse of these x and y values. So c equals square root of negative 1.11 meters squared plus negative 4.89 meters squared. And like I said before, I'm going to go ahead and do these squares and figure out significant figures before I add. So this negative 1.11 is going to get me 1.23 square meters, and the 4.89 is going to be 23.9 square meters, okay, because I have to keep three significant figures, okay? So then when I add them, I have to add with significant figures to the least precise, and so I'll be rounding to the 10th, nearest 10th value. And so these added together, when then rounded to the nearest 10th, is going to be 25.1 square meters. And then we take the square root, and we're going to get 5.01 meters. So that is our C magnitude of that vector. Okay, now I am going to get the angle. So I'm going to use equation 4.3. The tangent of my angle equals, I'm going to take the y value of my c divided by the x value, negative 1.11 meters. So always remember y over x, and the easy way to remember that is just like we do slope, rise over run. All right, so the height divided by the distance horizontally. Now, like I told you before, I like to just go ahead and do all of this at once. And so I'm going to just cancel these meters and then rewrite this. Angle is negative 1.11 divided by, oh, sorry, I messed that up. The inverse of my tangent, right? And then negative 1.11 divided by negative 4.89. Okay, and so then when I do that, I'm going to be rounding to the to 3 significant digits, and we will get 12.8 degrees. Now, like I told you before, always, once I get this value, I'm going to check to see if it is in the right degrees or if I need to add anything to it based on what quadrant I am in. Okay, there's 2 ways I'm going to do this. One is more accurate than the other. Okay, so this what I drew here earlier, this C is telling me it's in quadrant 3. Maybe if I didn't draw it well, it's in quadrant 2, but it's definitely not in quadrant 1. And so I'm going to have some kind of addition. Now, luckily, quadrant 2 and 3 both have the same, and it would be plus 180. But let's go ahead and check the other way. So the other way is looking at our y and our x value that we got for C, okay? And so the y value is negative and the x value is negative. So that puts us for sure in quadrant 3. And so if we get a value that's in quadrant 3 from our calculator, we always need to add 180 degrees. And that is then going to give us a final answer of 192.8 degrees. And so writing this out, the sum of the displacement vectors is 5.01 meters at 100, oops, my brain's ahead of my hand, 192.8 degrees. That is my final answer. Question 12. A ship's captain gives her ship a velocity of 17.3 meters per second at 47 degrees. The current has a velocity of 3.4 meters per second at 231 degrees. What is the actual velocity of the ship? So, like before, I'm going to go ahead and draw myself a little graph to give myself a visual representation of what is happening. Okay, so the initial velocity that she's giving the ship is 17.3 meters per second, and it's at 47 degrees. Okay, so 47 degrees is about a little over halfway bisecting this. So that's my A. The current has a velocity of 3.4 meters per second at 231 degrees. So 231 degrees is going this way. And it's quite small compared to what the A is, right? 3.4 versus 17.3, right? So it's a small line. Okay, so this is my B, and this is my A. Okay, and so my B is going to be doing something from the A value, a little bit like this, okay? not necessarily drawn to scale, but just giving an idea of what is happening. Okay, and then my C would be like this. Okay, so now we will begin. Okay, I'm going to call my A value the velocity itself, 17.3, and that's meters per second at 47 degrees. I'm going to call my B value the velocity, which is affecting A, 3.4 meters per second at 231 degrees. Okay, and so now I'm going to get my X's and Y's from my A's and B's. I'll start with Y. So Y, take 17.3 meters per second. So this one I'm using equation 4.1, and we're multiplying it times the sine of the angle 47 degrees. And with that, I have to go to two significant figures. Okay, I have 3 here, 2 here, so we go with the lower one, and so it's going to be rounded to 13 meters per second. Let's do my B value Y. So here's 3.4 meters per second times the sine of 231. And again, I'm at two significant figures. I have a 3 and a 2, so we go with the lower one. And my B value is negative 2.6 meters per second. Okay, now let's do my X's. So here I'm using equation 4.2, 17.3 meters per second times the cosine of my angle 47. Again, two significant figures, and so for this I get 12 meters per second. My B value for X, 3.4 meters per second times the cosine of my angle 231, and for the B I get negative 2.1 meters per second. Okay, so now that I have the A and the B, Y and X values, I can calculate the C using addition. So my CY is going to be the addition of these two. So 13 meters per second plus negative, there gives a minus 2.6 meters per second. And so rules here with significant figures, I have to go to the least precise. So I'm going to be rounding to the nearest ones digit. And so I'm ultimately going to get, subtracting basically 3, and I'm going to get 10 meters per second, but I've got to keep significant figures in mind, and to denote that this is still two significant figures, I'm going to put 1.0 times 10 to the 1 meters per second. Okay, so that's my CY. My CX, same thing, I'm going to add these two. So we have 12 meters per second minus, because this is negative, 2.1 meters per second. And again, I'm at the nearest ones digit with my answer because of rules for subtractions and significant figures, and this is less precise. And so I'm going to get this, actually the same thing, 10 meters per second, which I'm going to denote more correctly by 1.0 times 10 to the 1 meters per second. Okay. So now I can determine my actual velocity of my ship, C, and the angle. So I'm going to use equation 4.4 to determine the velocity, which is just our equation for determining the length of a hypotenuse, right? And so I have these two 1.0 times 10 to the 1 meters per second squared plus 1.0 times 10 to the 1 meters per second squared. And those, when they are added together, or go ahead and do the squaring part first, right? For the first one, we get 1.0 times 10 to the 2 meters squared per second squared plus 1.0 times 10 to the 2, 10 squared, meters squared per second squared. Okay, and when we add those together, we get 2.0 times 10 squared meters squared per second squared. And then when we get the square root of this finally, we get 14 meters per second. So this square root, when you do that, it looks nothing like 14, but we have two significant figures here, okay? And so we round that to two significant figures. So now let's go ahead and figure out our angle. For this one, I'm going to go ahead and do that moving around thing first. Okay, so instead of saying the tangent of the angle, I'm just going to say the angle equals that inverse of the tangent times y over x. So my y is 1.0 times 10 to the 1 meters per second, and so is my x. Which is equal to 1 if you want to make it easier to put in your calculator, right? Okay, so once we calculate all of that out, the tangent of 1, and we will go to two significant figures because these are two significant figures, is 45 degrees. Okay, let's double check where we are at. The graph that we drew earlier shows that we are in quadrant 1, and so does our y value, which is positive, and x value, which are both, so since they're both positive, we are definitely in quadrant 1, and we don't need to change anything about the angle. So the actual velocity of the ship is 14 meters per second at 45 degrees. Remember, I haven't been doing my normal highlighting of vector quantities and things, but we are still talking about velocity, right? And so this is actually, what is the velocity? Velocity requires that direction as part of the answer. Question 13. An airplane needs to travel with a velocity of 756 kilometers per hour at 158 degrees. The wind has a velocity of 25 kilometers per hour at 268 degrees. What velocity should the pilot give the airplane? Okay, so this question is worded a little bit differently than what we've had previously. We are given what the velocity needs to be. So what the actual velocity should be, which what we've been referring to as c. And we're given how the wind is affecting it, which is what we've been referring to as b. What we don't know is what the pilot is actually doing to the plane, and that is a. Okay, so we're solving this in a little bit in a different order. Let's go ahead and draw this out. Okay, our C is at 158 degrees. So about like that. Okay. And our B, our wind velocity, is at 268 degrees with a much smaller magnitude. Okay, 7056 versus 25. So it's a tiny, tiny line. Okay, if we're drawing that from the point of origin, it's almost going to look like a straight line down, right? Because 268 is very close to this 270 line. It's just like, look like that, like tiny. Okay, you can't even probably see it well. But that would be our B. And so what is happening when we're drawing it over here, remember that B affects A to get to C, right? So this B should be pointed the same direction and pointing at the C arrow. And so it's kind of like this, okay? There's our B, and I can't even really label it because there's not enough room, but B, okay. And then our A is just going to look crazy close to C and make this look really much even more of a jumbled mess. There's A, okay. But what you should gather from this is, okay, yeah, A is going to be very close to what C looks like, and it's going to be happening in quadrant 2. Okay, there's no doubt about it. Now, what the actual numbers are, that's what we're going to find out. So let's go ahead and write all this down. So our C, what we're saying is C, is 756 kilometers per hour at 158 degrees. And our B is 25 kilometers per hour at 268 degrees. All right. And so now we can determine our Y values and X values for B and C. So let's start with C, do our Y. And again, once again, we're using equation 4.1. We're just plugging in C instead of A from that equation. 756 kilometers per hour times the sine of 158. And that's 3 significant figures. And we get 283 kilometers per hour. For our Y for B, we get 25 kilometers per hour times the sine of 268, and we get negative 25 kilometers per hour. Okay, let's do our X's. So CX, 756 kilometers per hour times the cosine, so we're doing X, of 158. And we get negative 701 kilometers per hour. For B, we have 25 kilometers per hour times the cosine of 268, and we get negative 0.87 kilometers per hour. Okay, this one seems weird, but it's 2 significant figures, and that is what that ends up as with 2 significant figures. Okay. So now we're going to calculate our A. Now remember, I'm going to write this off to the side. Our A of X, or we'll just say Y here. Okay, A of Y is going to be C of Y minus B of Y. Okay, because remember C equals B plus A. Okay, so we're just flipping it because we are needing to solve for A instead of C this time. So our A of Y is going to be 283 kilometers per hour. and it's a minus and negative, right? So we're going to put a plus here, but we are subtracting this, okay? So minus negative 25. So I'm going to say plus 25 kilometers per hour. And that is going to give us 308 kilometers per hour. So remember, with our significant figures rules, it's just to the least precise digit. They both are precise to the ones place. And so we just do a simple addition here. Nothing to worry about changing with significant figures on this one. Okay, so now our x, I'm going to do the same thing here, just use x values. So negative 701 for our c value. We're subtracting a negative 0.87, so I'm just going to put it adding here, 0.87 kilometers per hour. Now this one, we do have run into a significant figures issue. Our least precise is the ones digit, and so we're just going to round to the ones digit. And so we end up with another fun one that we have to use scientific notation for, a 7.00 times 10 to the second kilometers per hour. Okay. All right, so now we can find our magnitude of this velocity of A and then find the angle. Again, using equation 4.4, determining the hypotenuse of the triangle that has these two lines. So A is going to be the square root of 308 kilometers per hour squared plus 7.00 times 10 squared kilometers per hour. All of that squared. And I calculate that out. So when I do 308 squared, I'm going to automatically round it so that I only have 3 significant figures. And so when I round that, it's going to be 94,900. Okay. And then here, I'm going to have to continue using scientific notation, right? And so I'm going to get 4.90, keeping it with 3 significant figures, times 10 to the 5th kilometers squared per hour squared. Now, when I add this, the scientific notation is not super helpful for determining what I need to do with significant figures with the addition. So I'm just going to under here kind of write in parentheses what we actually have. So this is 490,000. Okay, so when we do this addition, we have to be to the least precise digit, and that is the 10,000s. Actually, that is also to that is to the thousands place. Okay, because this is the least precise digit. Okay, because of significant figures, this was a significant figure. Okay, so when I add these, I'm going to get 585,000 kilometers squared over hours squared. And when I finally take that square root, I'm going to get 765 kilometers per hour. And remember, I've rounded that to 3 significant figures. So that is my A. Okay, I'm going to do the same thing that I did previously when I'm determining the angle. I'm just going to go ahead and make it the angle equals the inverse of the tangent. to save a little bit of time. So my angle equals inverse of the tangent, and we're always y over x, right? So my AY is 308 kilometers per hour, and my x is a 7.00 times 10 squared kilometers per hour. Okay, these are going to cancel so that I'm left with a unitless number, and that number is going to be negative 23.7 degrees. Okay, we know it can't be that, right? And we know that we are in quadrant 2, both from here and the fact that we have a positive y and what did I do wrong here? Okay. I neglected to show that this is negative here. Yeah, so it's -7. And here, this didn't affect the A because the negative ends up being positive when you square it. Okay, so we got 7. Okay, and that's how I got the negative 23.7, because that should be a negative 7.00 times 10 to the second. Okay, so yes, so we are right that positive y and a negative x. You see, and so this is also me catching mistakes, and that's why I'm going to leave it in this video, because it's good to see your teachers showing how they catch mistakes too. Okay, so we're in the quadrant 2, so we're going to add 180 degrees, and we will get 156.3 degrees. So my final written answer here is the pilot should give the plane a velocity of 765 kilometers per hour at 156.3 degrees. Question 14. A ship is traveling with an actual velocity of 13.8 kilometers per hour at 66 degrees. The engines are giving it a velocity of 12.9 kilometers per hour at 59 degrees. What is the velocity of the current? Okay, so here we're given that this is actual velocity. So, based on what we've been doing, A is going to be what the ship is doing, B is what the current is doing, and C is the actual velocity that's happening with what the ship's doing plus what the current's doing. Okay, so this is C. Okay, and then the engines, this is A. So let's go ahead and write that out. C equals 13.8 kilometers per hour at 66 degrees, and A equals 12.9 kilometers per hour at 59 degrees. And so now that I've done that, I want to go ahead and graph out what it is that's going on. Okay, so let's do A first. So 12.9 kilometers per hour, very similar to what C is. It's going to be a little bit lower, 59 degrees. So just kind of an approximation. And we'll say that is A. Okay, then C is 13.8 kilometers per hour, so it's going to be a little bit longer than A at 66 degrees. So the angle is just a little bit higher. Okay, so that's C. And so then what B has to be doing is it's going from one to the other. Very small little line. That's like that. Okay, now if I were to draw it from the origin, it's probably going to look something like this. Okay, and so we are looking for something that is probably in quadrant 3, unless I wasn't great at drawing it, and we'll find that out more specifically when we do these calculations. Okay, so let's figure out the y values of everything here. So y values, we use sine. And so for the y value for C, we have to use 2 significant figures because of the 66. And so we get 13 kilometers per hour. For A, same thing, we're going to get 2 significant figures. And so rounding that, we're going to get 11 kilometers per hour. Let's do the x values using cosine. Here, 2 significant figures as well for the 66, and we're going to get 5.6 kilometers per hour. For the A, not y, x value, two significant figures will get 6.6 kilometers per hour. So now we're going to determine what the B, Y, and X values are. And so just remember that, C equals B plus A. And so to get B, we're going to do B equals C minus A, okay? So for BY, we're going to have 13 kilometers per hour minus 11. And 2 kilometers per hour for our BY value. For our BX value, start with 5.6 kilometers per hour. And we're subtracting 6.6 kilometers per hour. To get negative 1.0 kilometers per hour. Okay. So now that we have y and x, we can determine what b is using our hypotenuse formula. So we have 2 kilometers per hour squared plus negative 1.0 kilometers per hour squared. Of course, that's going to give us 4 kilometers squared per hour squared plus 1.0 kilometers squared per hour squared, which this has 1 significant figure and the precision is to the ones place, and this is to the tenths place. So our answer has to be to the least precise, so to the ones place. And so we're just going to get 5 kilometers squared over hour squared and get the square root of that. Now, when we do the square root of this, it can only be 1 significant figure because we're using the rules of multiplication and division. And so that ends up getting rounded to just 2 kilometers per hour. now let's determine our angle. And so as I've done before, I'm going to just kind of shortcut here and say my angle is the tangent inverted of y over x. And so for my y, I have 2 kilometers per hour divided by negative 1.0 kilometers per hour. Okay, so essentially my inverse tangent of negative 2, right? And I'm going to end up with negative 60 degrees, which is obviously something I cannot use. As I predicted, I'm in the second quadrant, and that is confirmed by my by value being positive and my bx value being negative. So I'm going to add 180 degrees and end up with 120 degrees. And so my final answer here is that the current is 2 kilometers per hour at 120 degrees. There we go. So as always, if you have any questions, feel free to post them in the comments and I will do my best to answer them.